Hello everyone. In our last video, we learned some probability rules that had to do when we are dealing with one event or another event, and we called it the addition rule. We also learned the complement rule. In this video, we're going to learn a couple of more important probability rules. One has to do with what's called conditional probability, and the other one is the multiplication rule for independent events. When we say conditional property and we're dealing with two events, then, for example, the conditional property written as P, as we have right here, P of E given F. So this symbol right here will be written as, you know how in set builder notation we read that as such that. In this notation, we read it as given that F. So in other words, what's the probability of event E if we assume that event F has occurred, right? Here they're saying occurs. I think a better way of thinking about it is to assume that EF has occurred, right? So then we want to see what the probability of E is going to be. So we're going to look at a couple of examples that will make this very clear. Two-way tables provide a really fantastic opportunity to describe the notion of conditional probabilities. So here we have a total of 989 randomly selected adults who were asked whether they are interested in international news. This table that we see down here basically compares the responses. Notice that we have in the rows the type of interest, very interested, moderately interested, not at all interested, and in the columns we have the age groups of the individuals surveyed. So basically notice that we had 226 respondents for very interested, 462 for moderately interested, etc. Right? Here you can see the sum of the different kinds of responses, right, for the different age groups. All right, so let's see if we can answer some questions. So the first thing we're going to do is find the probability that one of the individuals in this survey being randomly selected being one of those who is very interested, right? And then we'll do a conditional probability. We'll find the probability of the individual being very interested given that they're in this age group, right? And then we'll compare the results. So let's first talk about the probability of very interested. So here we're going to be looking at this group in here, and notice we have 226 very interested individuals out of a total of 989. So the probability of very interested is going to simply be 226 over 989. We'll go ahead and calculate that on a calculator. So we have 226 divided by 989. Oh, not that. All right, my calculator is not cooperating. Okay, now it is. So 226 divided by 989, and we end up with approximately 0.229, right? So if we just go to two places, all right. Now let's take a look at the probability of very interested given that one of these individuals has already been selected, right? So What this does, this is the really important key thing to understand when it comes to conditional property. When you place a condition on the probability of an event occurring, you're changing the sample space of that event. So in the beginning, when we say what is the probability of very interested, we're looking at the entire group, right? So our sample space has cardinality 989. That just means the size of the sample space is 989, right? But notice that once you put the restriction, in other words, once you say you only want to consider these people, right, the 56 to 89-year-olds, then you're going to be looking at that sample space size, right? So you're going to be reducing the sample space. So now we're going to only look at this column, right? And we're going to see 106 very interested out of 370. So we'll go ahead and calculate that again on our calculator. So we have this time 106 divided by 370. All right, so we get approximately 0.286. All right, so what does a comparison of these two results tells us, right? Tell us. Well, it tells us that if we were to randomly pick a person out of the whole group, right, the probability that that individual is going to be very interested is less than, or a lower type of probability, smaller probability, than if we were to pick only out of the 56 to 89-year-old group, and of course, younger people usually have other more local interests, right? And then, as you get a little bit older, you start to get more of a global perspective, probably. So this tends to make sense according to just common sense as well, right? All right, so that's a really good example showing you the difference between the probability of an event versus the conditional probability of the event given a particular occurrence, okay? One thing that I really would like you to pay attention to is the fact that this is not invertible. In other words, the probability of E given F is not the same as the probability of F given E. All right, this happens quite a bit, and it's called the error of the inverse, right? So make sure you don't make that mistake. Here's a really nice example to get that point across. Suppose that event D refers to it being dark outside, right? And event M refers to it being midnight, right? Notice that if you find the probability of the event D, meaning what? The fact that it's dark outside, given that it's midnight, right? At any location you may happen to be in on planet Earth, right? Notice that that probability is pretty much going to be 1, right? Because at midnight, no matter where you are on Earth, it's going to be dark, right? So, however, notice what happens if we switch that around. If we look at the probability of it being midnight, given that it's dark outside, right? That probably comes down to practically 0. Well, from all interesting mathematical perspectives, we count that as 0, because think about it. And this is what confuses people. They think, well, look, the period of time that it's dark is only a finite number of hours, right? So why would you say the fact that you pick midnight is going to be such a rare thing that you say the probability is 0? Because remember, it can be dark outside, yeah, for a finite number of hours, but think of all the instances which it is dark, right? And this is a confusing thing for a lot of people, but it's no more, you know, strange than the fact that if you take any two real numbers like 0 and 1, right? How many numbers do you think there are between 0 and 1, right? You may be thinking a lot, right? Well, there's a half, a third, a fourth. You would be correct because there are actually infinitely many numbers between 0 and 1. Here's a very simple procedure that will generate infinitely many numbers for you. Just take the number that's halfway between 0 and 1. That's what? 1/2, right? Now pick the number that's halfway between 0 and that new number you found. So that would be what? 1/4, right? So here we have 1/2, 1/4. Now you can do the same with 1/4, right? Pick the number that's halfway between 0 and 1/4, and you get what? You get 1/8, 1/16, etc., right? There is no need for this procedure to end. There's no particular requirement that you have to stop at any time. So there's a quick proof for you right there that there are infinitely many numbers between 0 and 1. In the same way, if you take the time between, say, midnight and 1 a.m., right? There are infinitely many instances, right? Between 12 a.m. and 1 a.m., midnight and 1 a.m., where you can be doing the observation and it will be dark outside, right? So the midnight itself, which is exactly 12 a.m., is just one of those infinitely many instances where it could be dark outside. Okay, so always remember the probability. This is the order here is very important. The probability of one event given a second event is not going to be the same as the probability of the second event given the first event. Here we have another example using one die, and we will see how this is going to work out for us with conditional probability. Suppose that a person rolls a 6-sided die once. What's the probability that the outcome is a 6, right? Given that the number is even. All right, so remember what the original sample space would be, right? The original sample space for rolling a die is 1, 2, 3, 4, 5, 6, right? If you just wanted to find, if it were a simple question, we just said, hey, what's the probability of rolling a 6? Of course, that would just be 1 out of 6, right? Or 1/6. Okay. But here they say, what's the probability of rolling a 6 given that you already know that an even number has come up, right? So they don't tell you what number has come up. They just say, look, an even number has come up. What do you think the probability is that it's a 6? Well, now remember, you're going to be reducing that sample size. So the new sample is going to contain what? The sample space now is only going to contain the 3 even numbers, namely 2, 4, and 6, right? So therefore, the probability of 6 given that an even number has come up will just be, notice, 6 is just going to be 1 out of 3 outcomes, right? So it'll be 1/3. Notice that by reducing the sample size, the sample space cardinality, we've actually increased the probability. As you know, 1/3 is larger than 1/6. In fact, 1/3 is basically twice as large as 1/6. If you take 1/6 and multiply it by 2, what do you get? You get 1/3, right? So that's what's happening there. So now we're going to look at the probability that the outcome is an even number given that the number is at least 4, right? So notice if you look at this sample space, that's going to be that's going to contain what outcomes? Well, at least 4. That means 4 is one of the numbers that's possible, and then 5, and then 6, right? So now we want to know the probability that an even number has come up given that one of these numbers has come up. Some number greater than or equal to 4 has come up, right? So we can actually write that using, remember that notation, we use a capital X for the result of an random experiment like that. So now we're going to look over here, right? And we're going to see which one of these are even. And notice 2 of them out of a total of how many? 3. So the probability of getting an even result, given that we know the result that has shown up is greater than or equal to 4, is going to be 2/3, like that. So again, we also reduced this original sample space, but this time we reduced it in this way, right? And also remember, we're looking for a different type of thing here. We're looking for an even outcome. And how many of those are even? 2 of them. Very simple, very important. Next, we want to look at the important concept of independent and dependent events. Basically, if the outcome of one event has some influence on the outcome of another event, we consider them to be dependent, right? So in particular, going in this order, if the probability of the outcome E given the outcome F is the same as the probability of the outcome E, we say that the two are going to be independent. Why? Because look at it. The probability of the outcome E, given that F has already occurred, doesn't change. It's the same as the probability of the outcome E. So that means F has no influence on E, right? So therefore, we say they are independent. Now, if these two are not equal, then F must have had some influence on the result of E. In that case, we say they are dependent. So remember, just to summarize in a way that might be easier to remember, E and F are independent if and only if P of E given F is the same as P of E, and events E and F are considered to be dependent if and only if the probability of E given F does not equal the probability of E. In other words, if F occurs first, then E, that's going to change the probability of just E occurring by itself. So therefore, F has some kind of influence on E. Therefore, the two events are considered to be dependent. Here we'll look at a few scenarios, see if we can determine just intuitively and rationally if the events are dependent or independent. So here we're actually going to determine if they are independent. So we will answer the question according to that kind of questioning. So here we have an experiment, which is an American adult is randomly chosen. All right. So the two events we want to consider are the person loses weight and the person lowers his or her daily caloric intake, right? So basically, think of it. What do you think the probability of E given F is going to be? Is it going to be the same as the probability of E, or is it going to be different? Well, let's see. Remember, you have to look at event F first, right? Because this is the event that we're assuming has already taken place before looking at event E. Now, think about it. If the person lowers his or her daily caloric intake, is that going to have an influence on the person losing weight? Common sense tells us that it should, right? So this should not be the same as the probability of the person just losing weight, right? So the probability of E, therefore, we would consider these to be dependent. So our answer would be, are these events independent? We're going to say no, they're not independent, right? How about this one? A person flips a coin and rolls a six-sided die, right? So the coin, the event E is the coin lands on tails, and event F is that the person rolls a three. So we want to know if the probability of E given F is going to be the same as the probability of E by itself. Now think about it. Consider event F first, because when you write E given F, you're going to assume F has already happened, right? So the person has rolled a 3, right? Is that going to have any influence whatsoever on which side the coin lands on, heads or tails? It has no influence, right? Therefore, here we say the probability of E given F is the same as the probability of just E by itself, right? Therefore, these two events are independent. Okay. Again, very nice, simple concepts, but also very important to understand. So here we have a very important, again, simple rule, but a very important rule. We want to know the multiplication rule for independent events. If E and F are independent events, then the probability of E and F, remember, this is the first time we're actually considering this and statements on their own, other than the cases where we had the two-way tables and we looked at the intersection of the rows and the columns, right? But here we can talk about any two events, and if they happen to be independent events, then the probability of E and F, sometimes instead of writing E and F, you may see this written as the probability of E then F, right? But of course, as long as they're two separate events, they could be taking place at the same time too. That's why we go and F, right? Is equal to P of E times P of F. So basically, you multiply the two probabilities to get the probability of one event and the other event happening either at the same time or in sequence, right? All right, so here we're going to look at a couple of examples. A person flips a coin and rolls a six-sided die. What's the probability that the person rolls a 4? So we can write this symbolically like this. The probability that they roll a 4 and the coin lands on heads, right? Like that. So basically, we're going to be asking ourselves, first of all, are these independent events? We've already talked about this, right? The fact that a coin lands on its heads or tails is not going to have any influence on what number the die basically rolls on, right? So therefore, these two are independent events, and we can go ahead and use the multiplication rule. So we're just going to say that's going to be the probability of rolling a 4 times the probability of heads coming up. Now, what is the probability of rolling a 4? Well, remember, that's the sample space of 6 items, and 4 is just one of those 6 items. So therefore, we are just going to have 1/6 times. Now, what's the probability of rolling, that the coin is going to land on its heads when you flip it? We know that that's going to be 1/2. So we get 1/12. So remember, we're saying the probability of getting a 4 from the die roll and getting heads from the coin flip is going to be 1/12. You can also visualize this using the tree diagram that I showed you before. So it's actually a very nice practice to do so. Remember, when you here you're going to be what's the probability of the person rolls a 4? So let's go ahead and look at the rolling a 4 first. So our first action will be rolling of the die, right? So we'll have 6 outcomes, right? So start here. We're going to do first roll the die here. So 1, 2, 3, 4, 5, 6, right? So we know the outcomes can be 1, 2, 3, 4, 5, 6. Now, no matter which one of those is going to be the outcome, when you flip the coin, then you're going to have 2 choices. So heads or tails, right? This is going to be a little bit tight here. Heads or tails. For the 3, we're going to have heads or tails, right? For the 4, 2 choices, heads or tails. For the 5, we'll also have 2 choices, heads or tails, as well as for the 6, right? So look, notice when you want to count the total number of possibilities, you're going to have, here they are, right? You could go 1H, there's one possibility, right? Or you could have 1T, right? Or you could have 2H, or 2T, right? You get the idea here. And 3H, 3T, 4H, 4T, 5H, (5T), and finally 6H, 6T. So notice 3 columns of 4, so that's 12. So if you wanted to actually write the sample space for this experiment, you would just write S equals, and you would list all those next to each other. So 1H, 1T, 2H, 2T, right? I should have done this from the beginning, but doesn't matter. 3H, 3T, 4H, 4T, 5H, 5T, and then 6H, 6T, right? So notice that 4H, which is what we're considering here, a 4 being the result of the die roll and heads being the result of the coin flip, is only one possibility out of how many? 12. So I'm showing you all this work up here so you appreciate the power of the multiplication rule. You see, as long as you know the 2 events are independent, you can just find the probability of one multiplied by the probability of the other event, and you'll get this without having to do what? All that work, which is what you would have done if you didn't have the multiplication rule, right? Very powerful. Of course, even if the 2 events are not independent, you can still do it. It just takes a modification of the formula. You'll study that in the full statistics course, which is even not that hard, but we just have to basically pick and choose what topics we're going to cover here, right? Otherwise, it would become a full-on statistics course, which is not what we want to happen. All right. So you should definitely be able to answer this next one on your own. So do pause the video, try it on your own, and then come back. 3 coins are flipped. What's the probability that all the outcomes are tails, right? And I strongly recommend not only that you use the multiplication rule, but also do the tree diagram that I've shown you, just like this. In this case, you're going to have 3 events following one another, and it'll give you a real appreciation for this rule. Okay, I'm hoping you're coming back after a long pause where you figured this out. So remember, we're interested in the probability of all the outcomes being tails. So tail and tail and tail, right? Notice that the events are independent, you know? When you flip a coin once, right, the outcome of that flip has no outcome on any other flip, right? So therefore, using the multiplication rule, we know this is just going to be P of t times P of t times P of t, right? So what is the probability on a single roll of getting tails? That's just what? 1/2. So 1/2 times 1/2 times 1/2 will give us 1/8. All right, so make sure you understand these before we proceed. All right, here's a nice example which will involve both the complement rule as well as the multiplication rule. So for the spring semester 2014, 57% of students at Bellevue College were female. If 4 students were randomly selected with replacement from the college during that semester, what is the probability that at least one of the students would have been female? So we say with replacements, that means after a choice is made, it goes back into the pool where the second choice can be made, right, etc., on and on. So basically, remember that the probability of at least one student being female is the complement of what? What would the complement of that statement be? If you don't have at least one student that's female, that means the probability of no students being female, right? So, which is the same as saying the complement would be, what's the probability that all 4 of them are what? Are male, right? So the probability of the number of females being greater than or equal to 1, right, is going to be 1 minus the probability of the number of females basically being 0, right? If it's not greater than or equal to 1, right? If there's not 1 or more, how many is there? That would have to be what? 0, right? F equals 0. So what does that mean? That's the same as 1 minus the probability that the number of males that are selected is what? 4. Remember, 4 are being picked. Now, the first one, remember, this is happening with replacement. So the probability of the first one being male, right, is just going to be the same as the second male being selected. So basically, we're going to have 1 minus. Now, first of all, notice that the 57% were female, right? So that means 100% minus 57%. I was working ahead in my head. This is going to be 43% were males, right? So that means what? That means if you randomly pick the student, what would be the probability that the student would be male? Well, it would be 43%, which you can write as 0.43, right? Same thing. What if I ask you, what's the probability that a randomly selected student is female? Well, that would be 57% or 0.57. But right now, we're looking at the probability of 4 males coming in a row. So the first one will be 0.43, and because of replacement, that's not going to have any effect on the choosing of the second one. So that's also going to be a 0.43, right? So basically, you're doing this. You're finding 1 minus the probability of male times the probability of male times the probability of male times the probability of male. You see? So, and of course, each of those is going to be what? 0.43, right? So we have 0.43, 0.43, 0.43 times 0.43, right? So 1 minus that. So here, you could either keep writing these 4 times, Or you could just say, let me continue up here, it's going to be 1 minus 0.43 to the power of 4. That's the fastest way to, oh, I need that decimal point inside, like that, okay? So we're just going to calculate that, and we should be good to go. So let's bring back our calculator. So we're doing 1 minus 0.43 to the power of 4. So 0.9, approximately 0.97, right? So what did we just discover? We just discovered that in this particular college, where 57% of the students are female, if you randomly select 4 students with replacement, that means after you pick one, the name goes back into the pool for the second pick, right? That's what replacement means. Then the probability of at least one of those students being female is basically almost 97%, right? Because remember, you can write 0.97 as 97%, same thing, okay? So it means it's extremely likely that you're going to select a female, and extremely likely that you won't select a female, right? There's only a 3% probability that you will not, one of those students will not be a female, and they will all be males, right? All right. So that pretty much wraps it up for us as far as the lesson is concerned. And next, I just want to look at a few selective problems from the homework set to make sure that you can handle all of those. Okay, so here we're going to look at a conditional probability. We want to know what is the probability that a person rolling a 6-sided die once rolls a 1, given that we know that the roll resulted in a result that was no more than 5, right? So that means what? When we say no more than 5, you need to analyze what that means. So let's look at the new sample. Now, the original sample space for rolling a die we know is, let me change my color for a second. Oh, we'll work with this. Okay, we know the original sample space contains 1, 2, 3, 4, 5, and 6, right? Now, the modified one for this requirement, all right, sorry, I had a little phone interruption there. Okay, so the new sample space, given this new requirement, is going to be S equals, this is the modified sample space. It's going to have no more than 5, right? That means, remember, no more than 5 means less than or equal to 5, right? So we know the outcome was less than or equal to 5. So 1, 2, 3, 4, or 5, right? So this is the sample space for which you're going to compute this probability, right? Now, of course, a 1 is only one of those 5 results, so we get the probability of 1 given that something less than or equal to 5 has been selected is going to be 1 out of 5. Very nice. All right. Okay, here we have a nice example with a spinner. Notice that we want to basically find the probability that the outcome or where the spinner stops, and remember it says it cannot end up on a line, one of these lines, so we're assuming it's going to always stop only inside one of the zones, right? We want to know what's the probability that the outcome will be 2, given that we already know that the outcome is at least 2. So that means we know an outcome greater than or equal to 2 has been registered. So take a look at the image. Notice that that means that the outcome has been either a 2 or a 3 or a 4, but not a what? Not a 1, right? So the easiest way for us to handle this is to go ahead and, as we've done this a few times with similar problems, is to break the circle up into equal numbers of parts using the smallest part we see. So here you can see that's a quarter, so that would be a 1/8, right? So we're going to break it into 8 equal parts. So like this. So notice that basically assuming that the spinner has stopped in this region, right, which is how much? Notice that's going to be the total area of under consideration, right? So that's going to be 7/8. And what's the area of the number we're interested in? We want to know when it's going to be at 2, right? Notice that's going to be 1/8 of the entire circle. So we want to know the ratio of 1/8 to 7/8. In other words, this area that I'll go ahead and shade in red. So this area divided by the total area that we first shaded in blue. So 1/8 divided by 7/8, that will be the probability that it's going to be landing on a 2, given that the outcome is 2 or higher, right? So here, that is just going to be 1/8 divided by 7/8, right? So that's 1/8 times 8/7. These cancel out, and of course we get 1/7, just like that. Okay, so find the area of interest. That's going to be this outcome divided by the area represented by this request, that it's greater than or equal to 2. So we know that that is going to be this much of the circle, which is 7/8. That's why that's the total area under the consideration. And notice if we were dealing with the circle itself and we didn't have the conditional probability, the probability of getting a 2, right, without the condition would have just been 1/8. But because we have reduced the sample space size, right, we're only looking at this region, not the whole circle, the probability of getting a 2 has increased, because notice 1/7 is larger than 1/8. Remember, if you keep a numerator fixed, then the larger you make the denominator, the smaller the denominator. So 1/8 is smaller than 1/7. So we have increased the probability by decreasing the what? The sample space size. And that's really nice and important to understand. For this next problem, we're going to look at a table describing the number of college students who attended either 2-year or 4-year public schools, and then their status in 2013. And the starting year for the 2 or 4-year institutions was 2007. So the first thing we want to do is find the probability that a student randomly selected from the study began studying at a 2-year public institution in fall 2007, given that the student was still enrolled at any college during the spring of 2013. So basically, remember, when you're dealing with the probability of E given F, you deal with F first. You look at F because that's what's going to be your restricted sample space. So the student was still enrolled is this row right here. So basically, this is going to be the row from which we will determine the sample space size. Okay, and so now we need to focus on the fact that we are looking for a student who began studying at a 2-year public institution in 2007, right? So right here, so basically we're going to be dividing that number by this number. The mistake that most students make, they do find that number, but they divide it by this one. That would be if they only asked you the question without the restriction. So now we've reduced the sample space to the still enrolled group. So we're going to divide 164 by 349. So 160, what's going on here? Let's see if we can get rid of this. So one second while I figure this out. Okay, 164 divided by 349. All right, so we want to pay attention to the rounding instructions, and as you can see here, we want to round to 3 decimal places, right? So that would be to the nearest thousands. So we have to look at the digit at the nearest 10,000s, and we'll see that's a 9. So we need to round up. So the 9 rounds up to 10. So this becomes 0.470. Find the probability that a student randomly selected from the study completed a degree or certificate by spring 2013, given that the student began at a 4-year private institution. So the restriction part, what restricts our sample space, is this part. The student began at a 4-year private institution. So we're going to actually be looking at 4-year private. So now we're looking in here. Okay, that's going to be the sample space size that we're going to concern ourselves with. Okay, so in here now, find the so we're going to be now looking for completed a college degree, right? So working in this row, so we're going to be picking this number and dividing it by this number. Okay, so let's see what we end up with. $329 divided by 445. So 0.7, if we go to 3 decimal places, we get 0.739. Okay, so find the probability that a student randomly selected completed a degree by this date. So it starts out very similar to the previous part, given that the student began at a 2-year public institution, right? So all right, so we're going to go ahead and limit ourselves this time to this 2-year public institution column. So let me go ahead and clear the other marks. So now we're going to be looking at that column, this being the denominator of any fraction that we find, because we're going to be restricting ourselves to that group. And we're interested in the ones who completed a degree by 2013. So again, we're going to be in this group, so we're going to divide 347 by 870. And when we round it to 3 decimal places, we get 0.399, as we can see here. All right, so of course, when you compare these two results, the one from the group that started out at a 4-year private institution is higher than the group that started at a 2-year public institution. So basically, what does that mean? That means those students who started at a private 4-year institution were more likely to complete a degree by spring 2013 than the ones that started at a 2-year public institution. And that's all there is to this problem. All right, so here we have two events, E and F, that are independent. We know the probability of E, we know the probability of F, and we want the probability of E and F. Remember, we do have a formula at this time for probability of E and F as long as the two events are independent. And these two are, so then it's a very simple formula. The probability of E and F is just going to be the probability of E times the probability of F. So we're simply going to multiply 0.3 by 0.7, and that's 3/10 times 7/10, so that's 21 over 100, which is 0.21. So very simple. Here we have the probability of obtaining 3 tails in a row when flipping a single coin 3 times, right? So you can either flip 3 different coins at the same time, or you could flip this, you could use the same coin, but then you'll have to do successive flips, right? So obviously those would be independent events, because the result of one flip does not affect the result of another flip. So the probability of basically tail and tail and tail, that's what we're looking for, right? So that's just going to be P of t times P of t times P of t. And each of those, of course, is 1/2. So we get 1/2 times 1/2 times 1/2. So we end up with 1/8. Okay. And of course, you could have also done this using the diagram method, the tree diagram, right? Your first flip, so we start the process here. The first flip would give us either heads or tails. If it's heads, then the second flip could be heads or tails, right? And if it's tails, you could have that too, right? And then each of these for the third flip, of course, also gives us a heads or tails scenario as well. Same here, right? So now, if you look at the sample space of this experiment, you work your way down the, tree diagram, and you can see here you would have head, head, head. That's one possible outcome of the 3 flips. or head, head, tails, or head, tail, head, head, tail, tail. You could write all those down and you'll end up with a complete sample space for the experiment, all the possible simple outcomes, right? So head, 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 and then head, head, tail, right? Etc. So these are, you're going to end up with 8 of these, the last one being tail, 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 right? And of course, this is the one of interest, basically, right? So, and notice that's just going to be one possible outcome of this 3-step experiment out of a total of 8, right? So that's how you would approach it. So now you can see how simple the multiplication rule for product of and makes it. You just multiply the the probabilities of each of those events. In this problem, we're going to look at a contingency table, which is another name for the two-way table, which cross-classifies medical school faculty by the characteristics gender and rank. Okay, so let's take a quick look at it. There we are. So we want the probability of R3, right? So that would be the probability of being an assistant professor, correct? So here we go. Notice that assistant professors of both genders make up 39,953 total individuals out of 98,048 total. So we're going to go ahead and compute that now. So 39,000 actually, 39 and 953 divided by 98,048. And we want to 3 decimal places, so 0.407, correct? Find the probability of R3 given that G1, right? Remember here G1 represents male, so when we have given something, we deal with that sample space, right? So we're no longer going to be looking at all 98,000 individuals, but we're looking at these 69,418 males. So we want to know what's the probability of being an assistant professor given that a male has been selected, right? So basically we're going to be restricting ourselves to this sample space size, and the class we're interested in is assistant professor, right? R3. So that's the number. So we're going to be dividing this number by that number to obtain our answer, right? So remember, when you do a conditional probability, you change the sample space, right? That's the key thing. So when you're dividing the number of favorable items by the number of basically the cardinality of the sample space, that number on the denominator is going to change the cardinality of the sample space. So, all right, so we're going to get 25,607 divided by 69418. Okay, and rounded to 3 decimal places, that becomes 0.369. All right. Now we're asked if the events G1 and R3 are independent, right? Now notice that those events would be independent if the probability of R3 given G1 would be the same as the probability of R3. Remember? That means G1 basically would have no effect on R3. But if you notice here, we just determined that the probability of R3 given G1 is different from the probability of R3, right? So that means G1 does affect R3, so therefore the events are not independent. Okay, that's how you determine whether two events are independent or not. If you um, rewind back to where we discussed independent events, you'll see that this fits right in with that. Okay, because when this happens, that when the probability of one event given another event is equal to the probability of the first event, that means this event had no effect on it, right? So remember, here what we're saying is at R3 and G1 would be independent if this were true, right? But notice that this is not true. But the probability of R3 given G1 is not the same as the probability of R3 in this case, right? Because this one is 0.369, which is not the same as 0.407. So therefore, G1 does actually seem to influence R3. So therefore, we say that the two events are not independent. Okay. Let's look at one more problem before we call it quits. All right, so we have a six-sided die which is rolled 4 times. First, we want to know what's the probability of a 3 on the first roll, a 4 on the second roll, a 5 on the third roll, and a 6 on the final roll, right? The fourth roll. And remember, these are all independent events. What you roll, your first roll is, will have no effect on your second roll, right? So therefore, since they're independent, we're just going to get P of 3 multiplied by P of 4, multiply that by P of 5, and multiply that by P of 6. And of course, as you know, each of those events are going to have the same probability. When you roll a die, the probability of getting a 3 is 1/6. The probability of getting a 4, same thing, 1/6. So this is just going to be 1/6 times 1/6 times 1/6 times 1/6, which is basically just 1/6 to the power of 4, which is just 1 over 6 to the power of 4. And all we have to do is compute that. So we see that 6 to the power of 4 gives us 1296. So we get 1 over 1296, like that. All right, so find the probability of rolling all 6s, right? You see where this is going, because it doesn't make any difference what you ask for. As long as there's going to be 4 events in a row, they're all going to have the same probability. So the first one times the second 6 times the third 6, right, times the fourth 6. These are all going to have the same probability: 1/6, 1/6, 1/6, 1/6. So the exact same result as the previous case. All right. Compare the results. How do they compare? Well, obviously they're the same result. Student, let me go ahead and move these out of the way now that we know what they are. Student says the result you found in part B should be less than the result you found in part A because it is less likely to get all sixes than four different numbers. Of course, as you know, as far as probability is concerned, the student would be incorrect because the probability of both of those outcomes, is exactly the same. And remember, part A is also a very specific demand. You want exactly 3 on the first, exactly 4 on the second, etc. So this is no less likely than this. In fact, their probabilities are identical. All right, I think that you should be good to go for this set, and that should do it for now. So stay safe till our next video.